My name is Adrian Penicek. I was already introduced. I am a senior embedded software engineer at Cyclum. I work on different projects I'm not allowed to talk about, but yeah, I think you'd find them quite interesting. And I'm going to talk to you about software security. Just a heads up, I'm not a cybersecurity engineer, I'm the developer, which means I'm not the one that is responsible for investigation. So not everything will be 100% correct. So if you find something that is not correct, you can fix me in the chat. I'm not the one that is fixing back, I'm the one causing them. So without me, there wouldn't be any cybersecurity experts. So you're welcome. We rely on software on everything nowadays. If you think about it, not long ago, we only had some fat CRT TVs, which were completely analog. They are kind of black magic how they work. It's amazing. We had simple 555 timers. We had everything was using discrete components. But nowadays we came into an era, or maybe we're past the era of microcontrollers when everything can be made cheaper using microcontrollers. And now we entered the era of IoT. Slowly, we're at the beginning, I believe, because not everything is using some kind of IoT, but we're slowly getting there. And with that, there is a new kind of threat, I would say, something that we didn't realize before. No, because nowadays, once everything is connected into the internet, everything can be hacked. Everything is vulnerable. And before that, we didn't think much about it because, when we had our old Windows 2000 computers, Windows 95 computers, we didn't care about them getting hacked. What could happen? What would be the biggest impact if something got hacked? Yeah, we would lose our photos. Maybe we couldn't log into the computer. We would have some minor issues. Maybe we would have issues working, but it's about it. But nowadays we have, the photos could be like quite bad, but nowadays we have everything. We have power of multiple 95 supercomputers in our pockets, or even on watches. So we not only watches, also in earphones. If you think about how powerful are just AirPods from Apple, there's a lot of computing power within them. Something we couldn't imagine, or something that would take up whole rooms back in the days. And these kind of devices, they control our life. We can't imagine life without them. Once we lose them, once electricity drops, once the power drops or internet drops, we're lost. We don't know how to use maps. We don't know how to go anywhere. We don't know how to shop. We don't know how to meet with people. So we need to think about how to prevent these technologies from getting some kind of issues, or in the worst case scenario, getting misused against us. So let's go. I prepared multiple case studies. I talked about the high cost of software failure. Uh, I talk mostly about our personal devices, but not only personal devices are an issue, also the business devices. We have screens everywhere that people rely on them to find fire exit. People rely on them to find which kind of flight should they take, or anything is basically nowadays controlled by supercomputer, and people can't supercomputer, and people can't imagine living without it. So software failures are not just inconvenient bugs; it can be real issues. We can paralyze businesses. Bugs can ground flights. Bugs can disrupt essential services, or expose sensitive data, sensitive photos, and we definitely want to avoid that. And people don't think about that much until it happens. So the first case I would like to talk about is I would call it global paralysis, CrowdStrike error, which happened last year in July when I presume employee in CrowdStrike deployed a faulty patch into production, which caused multiple million devices over the world to fail and basically throw blue screen of that. CrowdStrike is basically a software security um, software that makes us feel safer than it's an I don't know specifically what they're doing. I assumed it's kind of antivirus, but this was not a malicious attack. This was just a mistake that happened, and it caused significant damage to their brand. So yes, that's something that could happen. We had blue screens of that on Times Square. We had blue screens of that all over the airports. Some airlines couldn't even fly; they had to ground their planes, and it smelled like $1 million damages. Maybe this isn't something that Rust would fix, but we'll get to something like that. So what are the issues? What can we face if any bugs occurs on production? What kind of issues can we face if there's a vulnerability within our system? Or yeah, we can lose brand image, we can lose clients, we can expose ourselves to potential lawsuits. It can range from a simple UI misplacement, something like a button missing, or login not allowed, or login failing, or servers completely crashing down and or not allowing users to do anything. But that's something that we definitely want to avoid. And I would like to divide for the people that are not so technically minded, what is basically bug and what is vulnerability. I would like to clarify that bug is something that is a flaw, but it's not put there by intention of making it a flaw. But vulnerability is something that is also not put there on intention, but vulnerability on the other hand opens up your code base to a attack from remotely or local attack from some kind of malicious actors. They want to abuse your system and push, maybe steal data, maybe crash it, maybe display some kind of wrong information or steal identities. Basically anything that is intentionally done as in a malicious intent. Okay, let's go to the second case study. This one is kind of scary, but I need to get your attention. This is the Terak 25, I believe it's pronounced like that, Terak 25. It's well-known case in developer community. It happened between the years of 85 and 87. And this was the reason that some people died. The bug that caused many people, not many, or 3 people to die and a lot of people to get harmed. What happened, basically, there was a device that was supposed to treat people with radiation, of probably cancer patients, mostly. And this device was deployed in America and Canada, and the United States and Canada, you have to be specific. And simply wrong UI, combination of a wrong UI, wrong commenting of code, and wrong, I don't know, operator error and human error caused that patients received 100 times the intended dose in some cases, and 3 people died from that. They got blasted with so much energy that their body couldn't recover from this. The whole system was coded. You can see that this is an ancient system. This is coded in before 1985. and uh, it was coded in PDP-11 assembly. So this is not necessarily a modern issue, but this is a good case study because it shows what can happen if we make bugs and if we don't think hard enough about fixing them and preventing them. There's a question from Ladislav. This wasn't caused by a buffer overflow. This was caused by, I would say, missing hardware interlocks and some kind of race condition. I can get a little bit into that. Basically, what happened that this machine had. I don't believe I have slide on that in the future. Yeah, I have. Okay, let's go to the next slide. Yes, that happened because of the race conditioning system. This machine operated in two regimes, and one regime was like a direct radiation, and second one was there was a plate that was inserted between a generator of radiation and the patient, which emitted electrons into the user. In case of this plate, when this plate was inserted, the intended dose was supposed to be much higher because it shielded the patient from most of its radiation, and only the electrons got into them. I'm not medical person, so bear with me. And what happened was that if an operator changed between those two regimes too quickly, this plate didn't have enough time to get into the correct position, and the software got stuck. And it reported back an error. It was called malfunction 54. But malfunction 54 doesn't tell you much. You would need to look up in some kind of manual or whatever, but there wasn't any. There was only a single person that coded this whole system, and they couldn't reach him. And because this system was throwing multiple malfunction error types, just operators just assumed everything was fine, but not in this case, because malfunction 54 was really the critical one that caused a large burning sensation within patients and loss of lives. If we think about that, yes, this device is from 85, but many of our devices that we use nowadays were still made in 85 or engineered in 85. For example, Boeing 737 Classic was engineered in the 80s, or I believe early 90s, around that. Many air conditioning units, many lifts, and many devices that are in some kind of industrial environment or some manufacturing plants or whatever, they were all designed in 85, 80 years and 80s. And there might be issues like that. But we didn't think much about the software safety back then. Let's change it. This one makes me chuckle every time because I made you kind of set on the previous case study. This one is funny. This was a tweet from a user called Johnny that asked, "What the heck? Why is my LG washing machine using 3.6 gigabytes of data a day?" Yeah, Johnny, bad news. Your machine was hijacked. Your machine became a bot in a botnet. This happens when some kind of hacker misuses or abuses of security vulnerabilities and hijacks the device, and they use it for basically like a VPN. You can imagine it as a VPN and forwards every network traffic through that, or either if it's for DDoS attack, for other kind of attack, or for whatever purpose. But yes, your washing machine probably shouldn't upload 3.6 gigabytes of data a day. It was a lighter note. Yeah. When was the last time you checked what your machine, washing machine on your internal network does? I never. Hopefully I don't have any device that is connected to the internet that I don't know about, but I try to avoid this. Okay, let's go for another one. This one is also funny. This was a CVE 2015-8370. We'll talk about CVEs later. but this was a case of a really simple, funny hack. And what happened was there is a software called Grub, which is a bootloader for a Linux subsystem, no, for whatever we want to use it, but it's promoted heavily for Linux. And it's open source software. It's deployed on countless machines, billions, I would say. And what it does is this one is the software that loads up first when you restart the computer, and then this piece of software loads up operating system. This is the simplest kind of explanation I can come up with. And this bootloader had a feature and still has a feature that you can lock it up with a password. And not many people use this because you most of the time you set a password for your operating system and you'll say that that's fine. But there is a possibility to set up a password for your Grub. And what happened was there was an error within the code that was processing the password. And if you pressed the backspace key 28 times, you could basically bypass that. This bug was there for 6 years. And this is like an open source project, one of the largest, or really largest. And many people looked into the software and nobody found the bug. But it's so simple, so funny that you could just, by pressing a key on your keyboard, hack and bypass the password requirements of the whole system. So yeah, let's try to avoid it. Yeah, it was, yes, Svetlana, it was about negative index. You basically were doing buffer underflow because when you pressed backspace, it would just go do like a -1 on a buffer when there was a password saved. And when it got over a certain threshold, it would just continue on the code without the password. You can search it up, or there's the index for the CVE. Okay, let's go for next. I would like to explain what the CVE is, because I try to make this presentation not specifically for developers or cybersecurity experts. This was also meant for non-technical people or not very technical people. CVE is a project organization that collects software vulnerabilities in their database. They evaluate them, or they give them rating for a severity and the impact, which means how probably are you going to get hacked with this vulnerability, and if you get hacked, what can the attacker do? Because there's a big reason. Yeah, you can get hacked and your attacker can change your desktop wallpaper, and that's not that bad. But on the other hand, you could be hacked and have your bank account stolen, and that's pretty bad. That's much worse than having your wallpaper changed. This is all listed on cve.org and exploitdb. What was funny, I found out today that they got their funding because the organization staying behind CVE was called MITRE. It was depending on US government funding, and they got cut. So I was afraid that whether I need to change this slide or not, but I decided to leave it in. They will still be working, and hopefully will still working as a proper tool for security engineers, cybersecurity engineers. Okay, this is the most annoying and most common argument. People just say, just go better. We've all heard it. True developers don't make mistakes. Yeah, true developers don't make mistakes. They just code everything on the first time and it works. And we just need to train the developers better. In some cases, yes, but not really, because even the best developers in the world, they make mistakes, and we don't want them And the best developers work on the most critical projects, and we don't want them to make mistakes. And the only way to help them is to develop tools that make them that help them avoid these kind of mistakes. For example, we'll talk about specific issues. I will be talking mostly about memory bugs because this is what we're focusing on. This is the most relevant topic on for the Rust community. So I would like to list most common manual memory bugs. If you've heard about some of these, you will maybe get bored on this presentation, but I won't get all over each and every one of them. But they're not sorted in any particular way. They're just listed because we'll use them in the future. I can talk about, for example, what happens if we use buffer overflow. If buffer overflow happens, in a non-technical matter, it's a space in a memory. You can imagine them like shelves or whatever, and we put some kind of items on that. And then if we have an item that we want to place, but we don't have a shelf for that, we don't have a place where to put it, then this might crash the system, and it might overwrite data on of other processes or the same process, and really bad things can happen. And we want to avoid this, so Rust is there to help us. So I don't want to bore you with technical specifics, but maybe we can talk about the integer overflow, because there was a really nice case study I didn't want to create a slide for. In June 96, there was a Ariane 5 flight 501, I believe it's called, which was a space flight done by a space experiment done by a European aerospace organization. I don't know what's their full name, but thanks to the integer overflow, they crashed, and it cost them like 370 millions of dollars or euros worth of damage. So yeah, it's simple bugs. This might seem simple. Yeah, I can explain what it is. Integer overflow is simple. We have thanks to how the computers work, we have a limited, we have like a ceiling for how big of a number we can count. And then if we go one over it, then we start from the bottom. So let's say we would have a place for maximum 100, the value of the number. And then once we go to 101, it will start a loop over to 0. Svetlana, you're asking, I saw the disassembly part how Rust handle integer overflow, but there are many such undocumented parts. Are there any presentation? Yes, we'll talk about this because Rust doesn't save us from integer overflow, not in all cases, but we'll talk about that. Okay, now it's getting a little bit more technical. No, a lot more technical, but just for a while, so bear with me, non-technical people. What is unsafe memory access? There is a piece of code. Everyone that has an experience with C should be able to find the bug in there. So try. I would like to test you. Can you tell me which line there is a bug? Did anyone find one?
Maybe there's no bugs at all. Come on, colleagues, feel free to jump in. What are your thoughts and observations?
Yeah, if you don't want to guess, don't want to embarrass yourself.
How can you printf a copy if you read?
Yeah, good observation, but there are multiple bugs inside.
With space in the end of cyclam, making it longer than the buffer?
Yes, the zero byte on the end of the string. Yes, on the line 2 of this source code, there's defined as. I'm sorry, I have a second monitor on such an awkward angle. It's defined as cyclam and exclamation mark, and there should be a reserve space for one more byte inside. But we're calling malloc, which is allocating a memory, but it's only allocating memory in the length of 7 bytes. and which means the whole string doesn't fit inside. And if we wanted to print this out, the system that will print out strings, it is looking for a 0 byte at the end, and it might or might not, but might crash and cause or list out the whole memory until it finds any 0 byte. Second issue was with the memset. The order of arguments is wrong. It would work. There will be probably some warnings from the C language, so from the compiler, but yes, that could be also pretty bad because the order of arguments is flipped. Basically, memset should go like we want to set memory in the copy pointer, and we want to specify in the second argument what should this memory be set to and how many bytes should we set to this byte previous to that. But in this case, we would set 0 bytes into the number of the value of 7. Yeah, there's next one that is not really a bug, but just a bad. I would say this is a bad language design because the character is specified to be const, but we can override it, which is like spec-wise this is okay, but C doesn't have immutability, which is kind of sad. And then we call the free, we call free on the memory that we allocated before, and then we try to get its value, which might or might not cause really big issues. Yes, okay. And as I said before, we're not the only ones to notice, because industry is sounding alarms. Many companies, large companies, Microsoft, Facebook, Google, they're saying that, yeah, okay, we might have issues because we still use C language for a lot of our code base. I would say we use C language everywhere, and I have a slide about that, about bashing C, or we don't want to hate on C, but we'll talk about it. But there's a significant percentage of bugs that are caused by this memory unsafe access, the manual memory management. And these are not just bugs, there are also vulnerabilities that are not really nice. One of the best maintained C projects is a curl. For those who don't know it, it's like a command line tool that can call HTTP or even other protocols, but let's say HTTP of another server, for example, if you want to, for example, simulate an access or opening some web page in a browser, but we want to do it in command line. That's just one use case. The curl is much more useful. But curl is an example of, I would say, the best maintained C code, open source C code ever. They have really strict rules on contributing, but they are still saying, as you can see the paragraph on the bottom right, we are certainly not immune to memory-related bugs, mistakes, or vulnerabilities. We count about 40% of our security vulnerabilities to date to have been the direct result of us using C instead of memory-safe language alternative. So they say 40% of their bugs are caused by manual memory safety, but some companies said it's 70, and some say 30, but still this is a large number, and if we can avoid it, we should. Same as companies, also governments sound alarms. These are clickable links, but I believe you can't click on the screen right now, but I will send you this presentation. These are links to some case studies, researches, and they provide really good information. And this is from the point of view of government and some kind of military safety and strategical safety, I would say. And as Neil Ziering said on the bottom right, memory management issues have been exploited for decades and are still entirely too common today. We didn't improve it. We still suffer from the same issues since the 90s, but now we have so many devices that run these kind of codes, so we need to do better. Okay, so are we bashing C? No, we're not hating on C. C is wonderful language. It's a little bit too old, yes, but C is the fastest language that we can code on, not in the sense of development time, but in the sense of runtime. Most of the performance critical code bases are coded in C, and I don't want to hate on that, but we need to fix that. We need to find an alternative for C, like ASAP, because once we start massively adopting IoT into our homes and have Wi-Fi chips in every light switch, then we can come into some serious issues. So yes, we can say that we can code in a higher level language. Yes, we can use Java, Python, whatever. But if you think about it, the runtime of Java, Python, JavaScript, it's still coded in C. So, okay, we can code safer code in Python, let's say, but if it still runs on a C runtime, we still have the same issues. We can't fix something that doesn't have like good grounding, good base. So we need to think about this real fast. Let's talk about Linux, because I was talking about how the best developers in the world make mistakes. And also Linux, the code base that is managed, maintained, and overviewed with so many experts, like the biggest experts. I would say the biggest experts in the world have some kind of footing in Linux. And there are still errors inside, and there are still ongoing null pointer dereferences. There are still ongoing errors. Just listed a few that I remembered out of top of my head. First one was dirty cow. It will be it stands for dirty copy on write, and it will be relevant later a little bit. But these are like big issues that cause memory corruption, privilege escalation, which is like the biggest issue, because Linux runs on most of our server infrastructure. And if we can somehow log into that system and get higher privileges and access, for example, virtual machines that are running on this system or databases, basically we'll just act as an administrator. That's a big issue. This was about the dirty cow, because this bug was caused by Linus Torvalds. Again, not to bash him, but I would say he's one of the best developers in the world at this moment. Not the best, no, one of the best. And he said this is an ancient bug that was actually attempted to be fixed once badly by me 11 years ago. So this dirty cow was there for years. And then before that, there was a similar version of the same bug, but it wasn't fixed, and not even the best developer could fix that because the tooling wasn't there. And the codes that are written within Linux kernel, they are quite complex. So it's not easy to maintain. So we need a better tooling. Many of the bugs and vulnerabilities that we come across nowadays, they are fixable. Or they are just something that we can prevent. And the reason why industries and governments are sounding alarms now and not 8 years before or 10 years before, the reason is that now we've shown that we have a good alternative for C language. We've shown that we have a better tooling, but we just need to implement it and just change our best practices. Yeah, we have some kind of ideas how to prevent most of the errors. Yeah, we have code reviews, or we try to avoid some kind of bad practices or code smells, and or we're trying to implement defensive programming. But the issue is that, this will not fix everything. We need some kind of automated tooling help for us. So here comes Rust. Let's talk about Rust. The first line is the most confusing from it, so let's get it out of the way. That's a broad level, and that's a term that I entirely made up, because we're talking most of the time about low-level and high-level languages, but Rust can also be really low-level and control microcontrollers. And on the other hand, its syntax can look really pretty, and we can do some kind of more advanced constructs on top of that. But I have a slide on there. We can talk about it later. It's a cross-platform. We can compile it for many microcontrollers, microprocessors. It works on all x86s, of course. It's compiled over LLVM, so with LLVM, so it runs everywhere that LLVM runs, almost everywhere. It is community driven. It's not maintained by a single company like C# used to be. It's open source, so we can all contribute to that. It's built on LLVM backend, as I mentioned. LLVM is a quite good alternative to GCC. It just takes a little bit more time to compile, but it's a really good compiler. And backend, I would say it's a backend. It's memory safe, which is the biggest benefit of Rust, and it has a C-level performance. A lot of people ask me, like, if we're talking of performance, because the C is its biggest argument is that it's the fastest. We can code the fastest code in the C, and in Rust we can get, let's say, at the same level of C, or maybe 5% slower. But is it really that bad if we think about it? We can talk about it later also, but it's not that bad, because our devices get faster every year, every month, I would say. And also the smallest devices that run with in our toothbrushes are still getting faster and faster, and I believe we can sacrifice a little bit of performance for getting a much more safer code in return. It's thread safe. This is kind of more complicated concept to show, but yes, and it's reliable. What I mean by that is that there is a compiler that we can rely on, and I'll show an example of that. Let's talk about history of Rust. Rust was originally developed by Graydon Hoare in 2006, but the Rust back in 2006 looked way different. It wasn't that good, but it slowly got improved, and in 2019, it was officially released as Rust 1.0 after Mozilla took over in 2009 the development. And also they run a big code base, or if you run Firefox, some parts of your code base run on Rust. I would say most of it. I'm not very sure. And then in 2020, big companies started to adapting it for performance and safety critical systems, mostly on the backend. And then in 2021, a big leap, Rust was partially adopted into Linux kernel, and it currently runs some kind of drivers for Apple hardware. Yes, we'll show that. We'll also talk about it. So industry and also governments trust Rust. You can see all of the logos on the left. I believe you can recognize them even faster than you can read them. So as I said before, Rust found place in the performance and safety critical infrastructure of most Fortune 500 tech companies. AWS, for example, uses it for S3 and Lambda services. Or if you don't know what Lambda is, it's a service where you can upload a piece of code and run within their servers. It's very scalable. It serves as a server, but it's on demand. It starts on demand. It isn't on some kind of server that is always on and waiting for input, but instead of waiting for input and having allocated one a big bunch of memory and storage for a simple service, the AWS spins up the virtual machine or container on demand, or once we get any request. It's really cool concept. Google uses it in Android on smaller components, not smaller, because I believe modern Bluetooth stack runs on Rust. And the next mention, because I didn't mention governments yet, DARPA started a project called Tractor, which stands for Translate All C to Rust. And their aim is to have some kind of tooling, we come up with some kind of tooling that can automatically translate all C code into Rust code. I don't know how far are they now, because that doesn't mean that the code won't need any adjustments, but should be mostly automatical. Because if we want to just translate the code, we will miss a lot of benefits that Rust provides us, such as some kind of modern constructs of development constructs and concepts. So DARPA. Okay, how does Rust do it? First of all, the most important is an ownership model. I have a demo on that on the next slide. We'll talk about it. Next is immutability by default, which means once we define something, we can't change its value. We can, but by default, its default behavior is we don't change it. It's forbidden, but we can force it to be mutable. Then we avoid null pointers, which was a big issue in the slides before. I mentioned the null pointer dereference as a big bug. So now we can avoid this because we use different concepts. We use options instead of some kind of null pointers that we always forgot to check. We have thread safe operations. As I said before, it's not really easy to grasp, but it's really there. We have smart pointers. This is nothing new. C++ has smart pointers since 2017, I believe. This is a good concept, so we don't forget we won't need to allocate manually that much. Instead, we can use smart pointers to manage the memory for us. And in Rust, this is also integrated in the basic tooling. Then we have integrated unit testing. This is a really good feature of the language, because on most of the languages, I don't think any other language has it like integrated within the platform itself. But we need to realize that unit testing is really important. There is no argument over that. And Rust includes it. Not only that they provide tooling for unit testing, their philosophy is that you write unit tests in the same files that you write your code. So you package it together. And unit testing in Rust is not an afterthought, it's a design choice. So this is really nice and really good for our future, for our safety. Then we have integrated package management, something that a C language doesn't have up to this point. We don't have any kind of way to include any or standardized way. We have like boost libraries and other types of libraries that we use to fill the gaps for some pieces of code that we don't want to code ourselves. For example, if we want to use HTTP on C, or we want to have a JSON parser, whatever, we would need to always use a library. But with Rust, it's much easier. The whole language is built with this package management in mind, and it works really seamlessly. And then the strict type system. C has a strict type system. Yeah, it's not like a PHP or JavaScript, but yeah, it's also one of the components that contributes largely into the safety of the whole system, the whole language. Okay, let's talk about ownership model. This is still the technical part. On the left, we can see the code written in C language, where we define a variable and we pass into the variable string that's saying hello. And then we basically try to pass the pointer to that variable into another pointer. And what happens is this is basically allowed. We can still access the first pointer that was defining the value. But in Rust, this is not allowed because we pass the ownership of the value. That's the whole idea of the ownership model. We pass the ownership to another variable, and this saves us from many errors, and also it makes us code much better. It's a good practice. Once you get used to it in Rust, you realize that you're doing this in every language, and your code is much cleaner. This is the error that is that is thrown by Rust compiler. Rust compiler, as I said, it has a really useful compiler. Rust has a really useful compiler that holds our hand. It will tell us not only that there is an issue, which is a typical C compiler approach. Yeah, you have issue. I can't compile that. There is some kind of, I'm expecting a different kind of syntax or whatever. Rust compiler directly tells us, yes, there is an issue on this line. If you want to read about this more, why is this an issue? Go to this documentation, and there provides a link. This is not like a whole output, but it wouldn't fit into the slide. But yeah, it's even much more helpful than this. It says, yeah, move occurred because S1 has string type which doesn't implement copy trait. It's a specific Rust specific thing, but copy trait basically means that we copy the whole value. Svetlana is saying in C we just assign pointer to the literal. Is the copy? What is the copy trait? Okay, I guess we have time. Okay, copy trait means that in Rust, not everything, but most of the things is struct or which we can derive. No, we can implement some kind of behavior on top of the struct, and the copy is like a specific behavior which tells us if we assign the value of this variable into another value, it will automatically copy the value into the other value and not move its pointer. We will not like move the pointer into another variable. We will copy the whole value into the new variable. This is the copy trait. And we can implement this on top of any struct that we would like to. And yes, yeah, it's like a copy constructor in C++. And we can implement this on top of any struct that we want to, and it basically means that the Rust will automatically copy the value and not copy the reference to that. Okay. There's the next example, which is immutability. I believe that everyone knows what immutability is. It's really easy to understand, which means that on the left, we have a example of C code where we define a variable of x. We've called x with a value of 5. We print up the value, it will say 5, of course. And then we'll change the value to 6. When we print out that, it will say 6. On the right, we have equivalent code in Rust. It's the same functionality, but this won't compile at all. As I said before, compiler will tell us, yeah, we're trying to change an immutable variable, and it's not allowed. And how to change that? Change the variable to immutable. We'll just prepend a mut before that, and it's solved. But yeah, that's a specific thing. I'll refer you to manual later. Okay, and null pointers. This is, I would not say that hey, I forgot to change the code on the left. Ignore the code on the left. I thought I forgot something before this presentation, but yes, this is it. And on the right, there is an alternative, which is an enum that holds. This is kind of a new concept. Enums in Rust are much more powerful. This is a direct quote from official documentation. Enums in Rust are much more powerful. And it says that this enum can have two values of none or some with a t. And t is a value. Basically, within the enum, we can pass along the value. And when we are trying to extract the enum, break it down, then the Rust forces us to like match for all cases, which means we need to handle all the cases of the return value. This is a more advanced concept, but it's really understandable from the documentation. I just wanted to show you how Rust avoids null pointers. I don't know that my explanation wasn't worth much, but we need to move on. We have a time schedule. Estoan, you are said, I call it my $1 billion mistake. And yes, null pointers are really a $1 billion mistakes. There is a lot to regret there. Okay, so let's talk about this more about the cost saving perspective from the manager's perspective. First of all, that we eliminate a lot of bugs by using Rust. These compile time checks I showed you before, these all happen before the code runs because of compile time. And this can prevent a lot of bugs that would otherwise occur on other languages. This is safer than, I would believe, any language out there, maybe except for Erlang. Next is that thanks to these preventions and thanks to the fact that we can reduce the number of bugs, then we can reduce also the downtime, because bugs cause downtime. And then we have also lower security risks and enhanced productivity thanks to the compiler that really holds our hands and helps us to develop a better code. Okay, there's a list of values. The title of the slide is Rust is safe by default. This may be a thing that I forgot to mention, because when we want to be really low, have really low level language, we need to have accesses to assembly language and the raw registers of a CPU and similar stuff. So the Rust provides us with capabilities to break out of its safety, out of its safety boundaries. But we need to go out of our way to break the safety of the Rust, but we can. And these are the bugs that are left over, which is a heap overflow, stack buffer overflow, and the integer overflow that Rust doesn't 100% fix, or that are not like 100% safe by default. But we can see how much this cute little mascot called, what is his name? Ferris. Yeah, his name is Ferris. And he scratched out most of the bugs out of the way. Which means if you think about it, these were the bugs that caused some projects said 40 to 70% of all the issues. So this is like solid reduction. Okay, next let's talk about performance. I mentioned before that Rust is like almost at the sea level, but not quite. But the reason is that it helps us to code more abstract features, and these might bring some kind of vtables and similar functionalities into the runtime. But yes, let's not talk about that. It's almost a native speed, such as C. It has a zero cost abstractions if we want to use only zero cost abstractions. It doesn't have a garbage collector. This is a big issue. For example, if you want to compare it with other languages such as Python or Java or name slipped out right now, the Google language. Never mind. It has fearless concurrency, which is kind of a new concept that we can code concurrent thread safe code, and we don't need to worry about race conditions if we do it properly. But by default, they are safe. I promised you I will explain what the broad level is, and broad level is the concept that we have some kind of low level languages that have like can directly manipulate the memory, that have a low abstraction, they have high performance, and they're compiled. And on the other hand, we have interpreted languages like JavaScript or compiled as Java, but they provide more of a more advanced programming concepts and data structures. But Rust can do both. It can really run the low-level code. It can run on microcontrollers, and on the other hand, it can still the code still can be really beautiful and on the level of Java. So how would we integrate it if we wanted to work with Rust? This is the thing that most of the companies that use C, they are quite conservative because, of course, they are, because they are using language from the 80s. So thankfully, Rust plays very well with other languages. It has properly implemented FFI, which is an interface to integrate other languages inside. And I have an example on my GitHub. I'll give you a link to my GitHub. We can just start to rewrite some of the, maybe not the most crucial parts, but some of the parts of our infrastructure or some parts of our project into the Rust language, and do it gradually, so we don't have to start the whole programming journey from the beginning. Then we can start. Oh, there's a typo. We can start the new projects, or whenever we will need something new, we can start it to code it in Rust. And many managers are afraid that, yeah, people won't know how to code in Rust, and C developers don't know how to code in Rust. I think that many of them are eager to learn how to do that, and nobody wants to go back once they start. Like, I didn't hear about anybody that said, like, yeah, Rust is too complex, it takes too long to code anything, I want to go back to C. Nobody says that. And then we can gradually adopt the Rust and gradually change parts of our infrastructure. We don't need to switch everything to Rust at this time. We just need to start now. As I said, this was a approach selected by a Linux kernel. It was implemented in the first Rust, Rust supporting a Linux kernel was released in the late 2022. And a slide before I said it was integrated into Linux in 2021, but that was the start of development. The first kernel integrated in Rust is kernel 6 version 6.1. And the most important thing is the largest thing the Rust is used for in Linux kernel is the Asahi GPU driver. That is a GPU driver for the ARM architecture of Mac computers. So if you run Linux on your Mac computers, on your ARM Mac computers, then it uses this GPU driver. Okay. So give me a second. So what do we need to consider before we start to integrate Rust into our company and our workflows? The first thing is the learning curve. We need to teach programmers how to use Rust, but thankfully the documentation of Rust language is awesome. It reads like a book, and it's literally called the Rust book. And the next thing we need to consider is the talent acquisition. There isn't that much Rust developers on the market right now, but how do we change it? We'll make some of the developers Rust developers, and then there will be more talents for acquisition. The compilation times of Rust language are not that long, but they are longer than the C language. But I believe that's not a big issue, considering that we have much faster computers than back in the days, and most of the use cases, most of the code bases of written in C are not that big. And then the next is the ecosystem maturity. The Rust doesn't have some kind of standard or anything that would satisfy maybe automotive. So that's also a consideration that some kind of niche domains, or maybe if we code for some kind of legacy microcontrollers, microprocessors like a PowerPC, there might be compatibility issue. But I believe not in the case of PowerPC. So the ecosystem maturity is not there, but that's only due to the fact that C language was basically implemented for everything. That's like the baseline. And compared to that, everything loses. Okay, next slide. What do developers think about Rust? And they love it. They love it. If you take a look at any Stack Overflow developer survey they made since 2016 up to, I believe, 2025, it will be the same. They have a chart that says what is the most loved, and recently they changed it to most admired language, and Rust wins since 2016 up to this date. So it's the most loved or most admired language between the developers. Rust has really good documentation. There's no doubt about it. It reads like a book. Some of the concepts that are a little bit more difficult to grasp are explained pretty well, but that makes it easier to grasp. And the better compensation, which is not that good of an argument. Yeah, Svetlana, you're asking about standards. Not yet. But the Rust develops really well. The development of Rust, the developers, they make a pledge that they will not break backwards compatibility. So I believe that as the language develops further, then we will reach some kind of standardization, and that would mean that automotive or military sector might pick this language up. Okay, and the last part is the better compensation. This is not a good argument for managers because they will need to pay more for the Rust developers. But yes, Rust developers make 17% on average, 17% more than C developers. Maybe the reason is that only the more skilled developers really tried Rust, so that is the reason. But yeah, if you're a developer, you might get paid more if you code in Rust. And yeah, some motivation to embrace the safer future. Explore, experiment, engage, educate, evaluate. Explore. Let's start just by reading the documentation because it's really, really well written. Experiment. Let's try to make some kind of small project. It doesn't need to be big. If you like to make calculators, or if you want to make some kind of standard Linux tooling, just recode anything. Like, I don't know, if you want to code ls in Rust, or you want to code some kind of terminal or whatever. That is the reason it was a good meme a few years before that. People are just trying to code everything in Rust now. And that's because they picked up some kind of small project they wanted to try to program in Rust. And there is a lot of alternatives of standard C coded projects and toolings coded in Rust. For example, you can find a lot of tools that are in a standard GNU distribution. For example, you can find ls coded in Rust, as I mentioned before, or cat or grep. You can find them coded in Rust on GitHub anywhere. But yeah, that was why a lot of projects were popping up with just saying, yeah, I did what was working before, but now I did it in Rust. Okay, next, engage. There are communities of Rust developers. Even there are local meetups, even in Bratislava, here in Slovakia. There are Discords, there are forums, and people are mostly helpful. So that is nice to see. You could invest in training and learning, but most of the time the documentation is just enough. And evaluate, which means just try it. And I'm sure you won't want to go back because it just works. Okay. On that note, I would like to end the presentation and ask if you have any questions. I have a small demo for you, but let's go over this.
I think you've covered all the questions in the chat. But colleagues, if anything else pops up to your mind, please turn on your microphone and ask the question to Adrian. Maybe in the meantime, while colleagues are thinking, maybe you could show the demo. Yeah.
Give me a second. The demo is not. Sorry, the demo is not coded in Rust, but it's a funny demo because this was not. This was aimed more about the software security. It's called cveroulette.com. And if you open it, there is a small project. It's open source. You can find. I made it with the help of my colleague because he wanted to get some practice in development, some experience, and you can open this web page and just click spin, and it will list out a random CVE from the CVE database, a random vulnerability. And it will show you on a scale of 0 to 10, what is the probability that this vulnerability was caused as a side effect of manual management of memory. So what is the chance that this is made by, was caused by a manual memory management bug? And this was done by loading all 200,000 of vulnerabilities, running them through an AI, and letting the AI decide whether this is a memory vulnerability or not. And then we serve these back on a website. And when I was thinking about it, I said to myself, yeah, this would be a really good drinking game. If you get anything above 6, it's your turn. But I'm kind of lucky right now, I would say. This is just a bunch of ones. Yeah, and there it is, 7.
Can you share the link in the chat with our colleagues right now? We'll definitely add it to the follow-up, but for everyone who's still with us on the call, who has survived until this moment, that would be helpful.
Yes, this is the link.
Great. Thank you. We will definitely have it in the follow-up as well, but still something for you to take a look at and inspire in the other way, how not to do. Any other questions, maybe, colleagues?
And if you have questions about Rust or anything,
Yeah, I have small question. Regarding Unwrap. So AI, like Copilot helper told me that, for example, Unwrap is not very suitable for production environment. So the question is there any kind of unwritten guidelines or best practices for Rust? Maybe some resource?
I believe that now if you turn up the warnings on Rust compiler, then it will say that unwrap is not allowed. But this is the one of the issues of Rust language we're talking about. I'll just clarify for everyone. Unwrap is basically a method that is implemented on the option type and the result type, as I mentioned before, the type that the enum that allows us to avoid null pointers. And this method basically says that if there is not a value, or if it's not the type with a value, then it will panic the whole system. But in some sense, this is a acceptable there are acceptable use cases for that. I, for example, use it even in my, as I said, this is not coded in Rust, but if you click over and look at my GitHub, there is a project that I wrote a chatbot hosted on a HTTP on a microcontroller on a ESP32. And I use Unwrap there. The code is not like the best code in the world because it was made to be familiar to C developers, but that's beside the point. Unwrap is really valuable in some cases, but this is the thing that you will need to catch as a code reviewer, because I use Unwrap in the code base because I want to deliberately crash the system if there is in some cases non-value returned. For example, if there is no configuration or whatever, I just want to crash the system. I would much rather use expect, which does the same as unwrap, but just types out the message that you put inside. But yes, did I answer your question? Because yes, the best practices are not do not use that, but there are some use cases where this is really useful piece of code.
Yeah, thank you very much. And a small another question: how often do you see object-oriented code in Rust projects?
Well, Rust isn't like it's not object oriented, but
you can-
it is in some sense because it has an instance of a struct could be called an object. But it's not not a standard OOP language because we don't use inheritance or polymorphism. Yeah, in some sense we use polymorphism, but yeah, I seen a lot more complicated projects and more complex projects. I myself write one. Oh, that's a proprietary one, but I'm not sure how to answer your questions because yes, there are projects that require a higher level of abstractions, and I've seen them many times. But I will not call this a object-oriented language because there's that's maybe just a nomenclature, but yeah, I would not call that a object-oriented language.
Okay, thank you. That would be great to see some examples of, abstraction, like complex code and what's abstraction in Rust. So if you have in mind, that would be great if you can share in the chat.
Try to find something.
And if you find it, Adrian, we'll add it to the follow-up. Or in the presentation, like that will be as a part of the links.
Yes. If you have any questions in the meantime,
Yeah.
I'll take a look at it.
There's a question from Usama. As a GIS developer, I use Python mostly. Should I learn C first or directly go to Rust?
It's not. It's a good idea to know C because it will help you to learn Rust faster. But we're at the point where I could say that you can go directly just learn Rust. But that means you will have a harder time if you don't understand the lower level concepts, such as what is like a size of a variable, what does a U32 mean, what is unsigned integer and stuff, because this is a concept that Python abstracts, and you will have harder time understanding Rust out of the box. But I will try that either way to go that way.
Thank you, Adrian.